So welcome everyone. My name is Eneko Aguirre. I am the head of the ITS Research Center, who's organizing this language technology webinar series. And today it's my pleasure that we are having Sam Bowman. But I wanted to point out that we have in this series Odette, Roger, Desmond, Dan, and then it will go on in May and June. And you can follow the instructions if you want to be up to date to the following seminars. So Sam is faculty at NYU since 5 years ago. He had before completed his PhD at Stanford, and his research focuses on data evaluation techniques and modeling techniques from sentence and paragraph understanding, and also machine learning to scientific questions in linguistic syntax and semantics. He's probably best known for coordinating glue and the super glue benchmarks, which received the EMNLP Best Resource Paper Awards and several other awards. And I have to say that I have the pleasure of visiting NYU, so I have known firsthand his group and the great work that they are doing. So when you want, Sam, I'll give you the rights. Should take just a minute. Okay, I need to find you in this long list of participants. And yes, now you can present.
All right, thanks so much. Let me set this up. All right, is it sharing only one window or it's multiple? It's doing something very strange.
Yes, so we see one window, but the slide is actually doesn't take the whole window.
Okay.
Just like
75%
of the window.
All right, how's this?
Yes, screen? Now it's full screen.
All right, the controls are a little weird, but all right, this should work. Sorry, yeah, I had to change computers last second. Cool, all right. Thanks everyone for coming. Thanks for the introduction, Eneko. It's been great having Eneko around at NYU. It's sort of jointly with Kinkin's group and the larger NLP group here. All right, so I'll jump in. So first, I want to say I'm presenting entirely about a position paper, so I'm going to be giving arguments, but very few, almost no new results. So I just want to quickly start with a kind of detour about what the more day-to-day, more empirical research out of my group is like. And so these are things that I'd be happy to talk about if you want to send me an email and chat after this. So we're working on a bias benchmark for question answering, trying to kind of come up with sort of realistic questions in a reading comprehension question answering system that are likely to trigger biases that will cause actual harm in systems. That's been a whole interesting maze of many, many different kinds of issues to figure out to try to get things together there. Working on long passage reading comprehension QA over something maybe the length of a magazine article or short story, sort of thousands or even tens of thousands of words. Explicitly trying to come to target questions that require you to understand the whole passage where no sort of single hop or multi-hop strategy will work. We're interested in generating arguments for QA answer choices, this sort of human-machine collaboration approach to difficult QA. And then we've got a lot of work on just kind of crowdsourcing methods. And one recent example of that is a study trying to collect very, very similar data across MTurk crowd work and Upwork sort of contractor style crowd work and just hiring NYU undergraduate students. So that's the kind of thing I've been working on in the lab. Anyway, on to the main body of the talk, this position paper. So I assume pretty much everyone here works in NLP, and I assume you'll acknowledge that hype is a pretty long-standing problem. It's probably getting worse. It's an issue. So this includes media hype. If you read the paper that this headline is based on, you'll know the headline is completely insane and totally divorced from reality. You'll see hype in published papers. This is a paper that actually made a pretty serious technical contribution, but the title they chose was, I think, quite misleading, and several papers came out afterwards explaining why it was misleading. And also, I'll take some blame here. Leaderboards and test sets can contribute to hype directly. These are numbers from Squad 2 and Superglue, both benchmarks covering roughly reading comprehension, both of which show that sort of 2019 era transformers were getting human level performance. This sort of implies, if you don't read the fine print, that we've solved reading comprehension, but there's plenty of evidence that's not the case. Here, for example, are much more discouraging numbers from the checklist paper, which is evaluating these same systems last year. All right, so this talk is basically about how we're reacting to this sort of hype cycle that's emerging in the field. So here's sort of the pattern that I'm seeing, that I'm arguing is happening. We've got this pattern of disappointing empirical results that show that state-of-the-art systems that we've been excited about, or that have been sort of promoted as very effective, turn out to be much less effective or much less robust than they'd initially seemed. And researchers very often, I think, completely reasonably react to this by adopting a pessimistic stance, sort of assuming when we're reading new papers, when we're discussing new papers, when we're citing work, when we're sort of introducing our own work, we make this assumption that state-of-the-art systems are much less robust or effective than one might think at first glance, and that effectively they sort of don't work that well. We sort of take this very pessimistic view of the state of the art. I think this is sort of, some form of this is justified in a rational response to the situation, but I think this sometimes gets sloppy, and this leads to misleading or unsupported claims. This leads to sort of negative claims about the state of the art that aren't responsive to new evidence. So I'm going to call this this phenomenon of sloppy negative claims underclaiming. I'm going to argue that it's fairly common and give 4 case studies of what this looks like. I'm going to argue this is more dangerous than it looks. They're sort of more harmful than it looks. This hurts our self-interest as researchers. It hurts our ability to prepare for the impacts of what we're building. And to get into a sort of the weird and speculative bit of the talk, if you accept that we are making progress in NLP and that it's possible to actually eventually get human performance on some of the tasks that we're working on, like QA, the impacts of what we're building could become much, much greater. And I think planning for those impacts is significantly higher stakes than just managing the impacts of what we have now. And then I'm going to very briefly talk about sort of what we do about this, how to try to get out of this pattern. I think it's pretty easy once we acknowledge the problem, but I'll make a few notes in that direction. All right, and also please feel free to interrupt me with questions or at least clarifications. I don't see chat, but I assume Nico does. I also want to just give this disclaimer. I'm trying to sort of walk this rhetorical tightrope here, where I'm arguing that underclaiming is common, that we're not taking certain kinds of evidence as seriously as we should when discussing new results. But I'm not trying to argue we've solved NLP. I'm not even trying to argue that we're making fast progress or good progress toward sort of general solutions to NLP. I think that's probably true, but I think that's irrelevant to the point that I'm making here. And I'm also not arguing that underclaiming is more pervasive than hype or more serious than hype. I just want to argue this is a real phenomenon. It's become pretty common, and the stakes are fairly high. So what does this look like? Let's finally get a little bit concrete. So the first example I'm going to give is about how we discuss sort of older negative results. And as a case study that I think is an unusually clear example of this, I'm going to talk about how we've been reacting to this John Liang 2017 paper, Robin Jia, Percy Liang. This is great work. I have no complaints about this work. I'm just going to be talking about how we react to it. So if you haven't seen this paper, they're evaluating models on the Squad reading comprehension QA task. And what they show is about half the time, they're able to trick systems by automatically adding this sort of junk sentence to the end of the paragraph that the model is being asked to read. This junk sentence doesn't answer the question. It doesn't give you any evidence that's relevant to the question, but it uses a lot of words in common with the question. And they find that when they add these junk sentences, about half the time the model decides to pull a possible answer from the junk sentence, which is going to be wrong, rather than finding the sentence in the passage that actually answers the question. So this is a pretty major robustness failure. It happens like half the time. But the enormous caveat to keep in mind when talking about these results now is that this was work done in early 2017 with studying models from 2016 and 2017. And those models predate modern language model pre-training. They predate Elmo and BERT and GPT and sort of that whole revolution in our capabilities. And this means that sort of these results aren't necessarily indicative of what would happen now. Just looking at results on Squad, our state-of-the-art systems have less than half the error rate of the systems that John Liang were testing. And I've got more discussion of this in the paper version of this talk, but if you actually run the same experiment with newer models, the results are much, much better. This effect here is only very slightly observable. And so this paper was very influential. It was, I think, an early prominent example of the kinds of robustness failures we should be looking out for as we start to think about deploying deep learning systems for NLU. It's been cited more in the last few years, in the last 3 years, than it was in 2017 and 2018, when it actually was directly relevant evidence about the current state of the art. And this is sort of harmless on its own. It's of course normal to cite work that was influential. But the trouble is, I think it's very common that in this citing work, you'll get this sort of, you won't get this mention that, by the way, we've seen this sort of transformative change in our technology since this came out. Here's one example from an award-winning paper. I'm not going to name the author. You can look it up in my paper if you need to. But it's one example of citing work that argues that current deep learning systems, when tested on cases sampled from a distribution that differs from the one they were trained on, their behavior is unpredictable and inconsistent with that of humans. And they cite John Young as evidence of this. This claim might be true, but I guess what I'm arguing is that for a paper that, for a recent paper, citing this older evidence, citing this evidence for sort of previous generations of systems, lets you get away with this sort of sloppy claim, lets you get away with making a claim without actually giving evidence. And even if this claim was true and the paper is written, you're not giving people the tools they need to find out whether the paper is sort of still true, whether this claim is sort of still true now, or sort of what generation of models, what technology this claim is true of. So I think a lot of these claims a lot of these citing claims are a little bit sloppy in a way that can be misleading. All right, next example is even a little bit more indirect, is one where I think there's no specific wrongdoing I want to point out, but I think is still an effect that actually can skew our perception and sort of discourse around the state of the technology pretty significantly, which is about sort of newer results on older models, especially newer analysis results on older models. So a lot of these results we see that are sort of deflating hype, these results, these sort of negative results, or these sort of results about robustness failures, come from dedicated analysis papers, things like sort of Bertology papers that download an existing system and sort of find new ways to experiment it, to find ways in which it might fail. And this work can take time to do, and it can take time to publish. And so there's often a pretty long time lag between when these results come out and looking back to when the original system that's being studied came out. And I think, especially with BERT, I think BERT has been sort of a magnet for this kind of work. These delays have gotten pretty long, I think, to the point that it is messing with the discourse a bit. So the one little bit of actual empirical work I put in this talk, I did a little 10-minute study of skimming some proceedings papers. So what I did is I looked at the NAACL 2021 analysis tracks. This is sort of top-tier venue for this kind of Bertology research or negative results research. And just pulled a random sample of papers until I'd accumulated 10 papers that studied existing models, that sort of downloaded and ran a system rather than training something new. 5 of those only study BERT, which came out in fall of 2018, and none of them study anything that was released since summer 2019. So if you were sort of at NAACL this year, and I think the results will be similar at ACL or MNLP, the median result you're looking at is for a system that's about 2.5 years old. And this may not be misleading. I think these papers do cite the work they're studying. They sort of give the year for the system that they're studying. But I think this can skew perceptions. If you go to a conference, you see sort of poster after poster for work that's showing that our systems are sort of have these major embarrassing failure modes. And then you walk down to sort of the next poster at the end of the line, and it's making these strong positive claims. If you don't notice this sort of pretty big temporal disconnect, this pretty big difference in sort of generations of systems that are being looked at, this can really sort of make it, this can sort of make one very, very nervous about taking seriously any newer results in a way that I think is not ideal. And I want to argue that for BERT in particular, this does really represent a missed opportunity. And this is something where, even if no one's doing something kind of strictly wrong, there's room to really do a lot better here. So what's special about BERT is that it defined this API, it defined this sort of MLM fine-tuning transformer standard that then lots of work has followed up on. So we have all these newer systems like Roberta and Albert and dBERTA that are better in really significant, sort of qualitatively noticeable ways where you might expect analyzing them to give different results than analyzing BERT, but they use the same API, such that any tool or technique or practice you've come up with to study BERT, you can really just sort of turn around and apply to these newer systems by changing one line in your code, just sort of changing what file you load or what you download. And to try to make this clearer, so I think this isn't always well enough appreciated, that these systems are really genuinely different from BERT and really are doing different things with language. Here's one empirical result that I think is pretty representative. So I'm always nervous about presenting test set results for sort of core NLU abilities. I think just the quality of our test sets is not great. I'm something I'm very anxious about. But I think if we're going to trust any test set result, the Winograd Schema Challenge data, this is data we used in Superglue, but from Ernie Davis's group here at NYU, I think this is the kind of thing we should be tending to trust. This is a common sense reasoning task that sort of uses coreference as a setting. The training set is very small. It's about 500 examples. There's not a lot of room to sort of overfit to the quirks of the data set design. The test set is out of domain. It was written by different experts at a different time. And all of the data was written by experts who were following a fairly long checklist of constraints to make sure to avoid any artifacts, any ways that the systems could easily cheat. Looking at sort of pretty straightforward out-of-the-box fine-tuning performance in this task, BERT is worse than chance. It's effectively at chance. It's BERT gets 54%, randomly guessing no, or guessing no all the time will get you 55. Meanwhile, dBERTA, sort of I think the best of these sort of post-BERT systems, gets 96%. So is essentially solving the task. So I think we should really expect that sort of negative claims we make about BERT aren't necessarily going to apply to dBERTA. And this is, of course, to say nothing of GPT-3, which from the evidence we have, it represents another qualitative leap over these sort of smaller scale BERT-style systems. Though, of course, sort of unlike dBERTA, getting full access to GPT-3 in order to apply some kinds of analysis is still challenging. All right, so that's the second case study, is the sort of long shadow of BERT. The third is diving into a sort of controversial discussion that's been going on in NLP lately about this Bender and Kohler paper that was the best paper at ACL last year. So this paper makes a claim that I think is basically true and was a useful claim to have made and defended. But this is, I think, the meat of the paper. This is the main argument the paper really sort of nails down with very clear arguments. It's that the language modeling task, because it only uses form as training data, cannot, in principle, lead to learning of meaning. So first I want to say this argument is straightforward. The way they argue this is by defining meaning, and this is a common definition, as a relationship between something internal to language and something external to language, as some kind of grounding out to perception or to maybe conceptual categories that are formed as a result of perception or interaction with the outside world. So in order to have meaning, you have to have something that is external to language and independent of language. And just sort of by that definition, a language model that only takes language input and output can't do this. So this is about as easy to prove as the argument that GPT-3 the GPT-3 can't eat a sandwich. It's really just all you have to know is that it's a neural network model that's just dealing with language, and you've got the answer to the question. This definition of meaning is a little bit controversial. A little bit of my background is in semantics, and there are some threads of research in semantics, both in NLP and linguistics, that adopt different definitions of meaning productively. But I think that's sort of one quibble I have with this. But I think that the bigger concern with how we think about this claim and how we react to this claim is that it doesn't make any predictions about possible model behavior on language tasks. For example, it's completely consistent with this claim that we might build a machine translation system that does very, very high quality translation, that has an internal mental model of how the world works, that it's sort of learned by reading language, and that it uses that model to do translation, that it really gets sort of near human levels of quality on lots of translation tasks. What we'd say in that case is that our translation system doesn't understand the language that it's translating, but that it turns out that you can solve translation without understanding. This is just taking this fairly narrow, fairly precise definition of understanding or meaning that rules out a lot of what we do in NLP. So again, this sort of potential positive result is not ruled out, or sort of this claim makes no prediction about whether these positive results like this are possible. But work that cites this paper, again, I'm more concerned about the work that cites this paper than about the paper itself. Often treats this claim as though it is evidence of some more concrete failure and some failure that applies to language tasks. So one citing work says that Bender and Kohler show that models are better in leveraging biased patterns instead of capturing a notion of language understanding for the intended task. I think this is not a fair description of what they actually showed. And for another example, I think is also fairly common, if a little bit stranger. Here's another quote from citing work. Bender and Kohler argue that the widespread belief that pre-trained language models understand or comprehend is hype. Based on the result of carefully designed thought experiments, Bender and Kohler show that it's impossible to learn the meaning of language by only leveraging the form of sentences. So this I think is more or less fair. I think this is basically true with some caveats, some clarifications. The problem is that this is a paper about regularization for language models. So this paper is proposing a better way of training a model on form alone. And this quote, I think, was in the introduction, was sort of setting up the work. And so the only way that the paper fits together, the only way that the paper is coherent, is if you misread this quote as arguing that current language models are failing to understand, but like better language models could solve this problem, which is not at all true, which is not at all what they defend. So effectively, if you read this quote correctly, then the introduction to this paper is explaining how this paper is sort of meaningless and shouldn't be done, which is not usually something you write in the intro to a paper. All right, that was the case study on sort of how we're discussing understanding and how that can lead to sort of somewhat skewed negative perceptions of what we can do. Fourth and final case study is on adversarial data collection. So the word adversarial means like 10 different things in NLP right now. I'm referring very specifically to an approach to collecting test data, specifically test sets, and the approach that was pioneered by Adversarial NLI, Beat the AI, and Dynabench. And this is this practice where you hire crowd workers to write test examples, and you give them sort of real-time interactive access to some sort of recent high-quality system, some state-of-the-art model, and you incentivize them to come up with examples that the system gets wrong, to sort of explore what the model can do and to sort of hit submit whenever they find an example that they think tricks the model. And so here's an actual UI example. The task is find examples that fool the model. The annotators are basically only paid when they find these examples, and the test sets that we're collecting consist entirely of examples that fool the model, after a little bit of sort of quality control, or maybe one or two additional annotators has to agree that the example is correct and does fool the model. So just looking at what I've only what I've told you so far, just looking at that sort of 3-sentence description of adversarial data collection, you can make some inferences about what results you might observe running some models on test sets that were collected this way. The most straightforward of these really just follows from what I just said, is that if you test a model on an adversarially collected test set, like adversarial NLI, and that test set was collected with that model loop, was collected to target that model, then the model will achieve 0 accuracy. Not chance accuracy, literally 0, because any examples that the model would have gotten right will be discarded and won't be allowed to be included in the final test set. So sort of at least some models that we're studying, which are currently state of the art, will achieve 0% accuracy on these test sets. And you can make those sort of reasonable inference. Making this precise is tricky, but you can infer that models that are similar to that system will achieve very low accuracy. So for example, if it's BERT base that was the target model here, you should expect BERT large to be only marginally better than chance, and maybe Roberta base to be only a little bit better than that, just to the extent that these systems are likely using somewhat similar representations and tend to make somewhat similar errors. And this claim about getting 0% performance doesn't assume that the models are brittle or bad. This is true even if the models are quite effective. So all you need to assume in order for this to work is that the model makes any possible errors or any possible debatable judgments on any possible inputs, just any string of the length that can fit into the model. So this really doesn't tell us that much. And this debatable judgments point is significant. For a lot of NLP tasks, including question answering and NLI, it's pretty easy to find examples that prompt legitimate disagreement among humans, where maybe if you get a group of people who are very careful, who are very thoughtful, who are fluent speakers of the language, and ask them to answer some question, just really reliably, 2/3 of them will answer it one way, 1/3 of them will answer the other way. That there's legitimate disagreement on what the answer is. And you can, if you run into examples like this during data collection, they can often pass quality control because you only need maybe 2 or 3 votes to accumulate a majority. And so you can wind up building test sets that are mostly full of these debatable examples. And this means that it's even possible to target very careful humans for 0% accuracy. If I if you run adversarial data collection where the model in the loop is just sort of me, Sam, frantically typing on the other end of a terminal connection, you can find examples where I disagree with a couple of other crowd workers and make a test set only out of those examples. And then if you test me on that, I'll get all of them wrong. So really, observing 0% accuracy tells you literally nothing about whether a model is any good. But you'll very often see claims that cite results on adversarially collected data that I think don't take this into account. I think this is often just a result of people looking at these numbers without reading anything about how the data was collected and sort of missing this really important caveat. You'll see these sort of negative claims framed a number of ways. This is maybe the most serious, the most egregious one I've seen. This is some citing work that's citing results on adversarial data that says that no actual language understanding is taking place in language model-driven approaches to these tasks, as can be shown by careful manipulation of the test data to remove spurious cues the systems are leveraging. If you think about where the data comes from and what this careful manipulation is, what they're arguing is that we're going to assume that current systems are cheating or ineffective. And so any examples the current systems get right can be thrown out as bad test examples. And then if we look at the remaining test examples, we see the model gets 0% accuracy. And so we can observe that the model is cheating or ineffective. And this is a completely circular argument. We had to assume the conclusion we're making in order for this argument to hold at all. So, all right. Each of these 4 examples is a little bit tricky, makes some assumptions, but hopefully you get some sense of the kinds of things I'm referring to, the kinds of sort of slightly debatable practices, especially in citation, that can give maybe an unfairly negative picture of what current state-of-the-art systems are capable of. And hopefully you can think of 1 or 2 other examples of where this kind of thing shows up. All right, so next I want to argue for why this is worth caring about, why this is not just kind of a curiosity or like a little bit of sloppy writing that's no worse than any other sloppy writing you'll see in science. I'm going to make 3 arguments ranging from the very sort of concrete and close to home to the much more speculative and out there, but I think also worth talking about. So first, the sort of close to home argument. Sort of just thinking about the health of NLP and computational linguistics as a scientific field. We'd like to think of ourselves as a science or as sort of an engineering science. In any case, we want to understand things and say true things about what computers can and can't learn to do with language. And accepting misleading claims doesn't help. One more concrete way this can harm us, kind of going beyond just like epistemology, is that if we take negative claims like this that are unjustified seriously, we'll often put effort and energy into trying to find solutions to problems that we actually have already solved, that actually aren't real problems anymore. Secondarily, just thinking about the health of the field, we rely a lot on funding from governments and industry labs, and from attention and sort of jobs from governments and industry labs. And this attention, this sort of interest from our supporters isn't allocated rationally, but it's also not random. And I think if really the consensus in the field, if what we're collectively saying when we talk about the current state of the art is that research is going in circles, that we're not making progress towards serious goals, that our systems, that our whole paradigm doesn't work, that sort of deep learning doesn't work, we risk that someone might believe us. And if they do, that's a pretty strong pressure to sort of stop putting so much energy into deep learning for NLP. And that, I think, risks sort of closing out opportunities for us to do work that is actually productive. The second argument for why this matters is thinking about current impacts of NLP technology. So our technology is starting to be deployed much more than it had been. It's having a fairly big impact on the world. Part of this impact includes avoidable harms, sort of real world harms that we have some obligation to try to mitigate or counteract. And a sort of classic example of this that I think is a good example is that sort of in most cases, pre-trained systems, these things like sort of Word2Vec or BERT or GPT-3, learn biases about things like race and gender that that we should be very, very careful about sort of letting interact with the real world. And in spite of this, people often deploy these systems in high-stakes settings like content moderation or resume screening, where these biases can cause sort of fairly concrete harms to people who didn't choose to use the systems. This is sort of the big thing that a lot of the field is anxious about, and that we do really have an obligation to try to mitigate. And this, I think, is a slightly tricky argument to make because at first glance, it looks like underclaiming might actually be helpful here, might actually help us get out of this mess. So I think there's this intuition that I've heard people state pretty explicitly in talks once in a while, is that if we argue that our systems don't work, if we sort of go up to the product managers who are deploying these systems in sort of recklessly or in the wrong places, and we tell them sort of, no, you don't understand. These systems, they don't understand language. They're not robust. They fail all the time. You can't trust them. If we tell them this and they believe us, they won't deploy our systems. They won't deploy the technology. And if they don't deploy it, then it can't do any harm. So this is a strategy that sort of could actually help mitigate these harms. But I think this is assuming that the people we're talking to aren't paying attention and have no memory. And it's just sort of, it's giving people too little credit in a way that makes this very, very likely to backfire. So I think what's going to happen if we do this is a little bit speculative, but hopefully you'll bear with me, is that if we keep telling people this, once in a while, someone will say, okay, I hear you. I hear that these systems are a disaster, but let me just try a small deployment. Someone deploys something and they see, hey, oh, our ad revenue went up a lot. Our customer satisfaction numbers on average went up a lot. Our retention went up a lot. Okay, these systems actually do work. Maybe I shouldn't believe what these academics, what these sort of more peer researchers are telling us about state-of-the-art systems. The stuff we can build in-house is actually great. And if we wind up in that situation, then even if we want to then go on and make these follow-up claims that, hey, by the way, these systems are also racist and biased in ways that make them really unusable for most applications, people will have already stopped listening to us and we'll sort of lose our opportunity to have that influence. So that's the second reason we should be nervous about this kind of underclaiming, nervous about sort of letting the consensus in the field get to be that the state-of-the-art systems don't work. The third argument, and this is where things get a little bit more speculative, and this is getting into stuff that I sort of have only been seeing more in the last year or so, is that we seem to be making progress. I think this is a little bit debatable, but it seems like our technology is significantly better now than it was 2 years ago, and significantly better then than it was 2 years before that. And I think it's sort of reasonable to extrapolate that, at least plausibly, in some number of decades, we'll actually start really solving these problems. We'll actually start building systems that are sort of genuinely robustly able to do language understanding and sort of reasoning with language in most domains. And if we do this, if we actually start sort of solving the tasks that we're working on in large numbers, the impact we can have on the world goes up really, really dramatically, for both good and bad. On the good side, you get sort of all of the classic things like Bowman and LP talk about when they talk about why they want to do this from an applied perspective. We could, for example, make it the case that anyone who speaks any of one of maybe 300, 400, 500 popular languages and has access to the internet suddenly has access to world-class education and world-class medical advice and world-class legal services and things like that. That would be really incredibly valuable. But we're also setting up, if we do this, potential sort of very abrupt, massive unemployment that'll be very, very hard to deal with. We're making misinformation campaigns or surveillance campaigns much, much more effective in ways that can really destabilize democracy. And we're opening up this potential for depending on who you listen to, really catastrophic risks, sort of really potentially incredibly destructive outcomes. So what's this catastrophic risk story? Like, what's going on here? This is this thing that I sort of wasn't really aware of until maybe the last year, that's this very unusual situation the field is in right now. So there's this pretty large community of researchers, mostly coming from philosophy, economics, and policy research, who are working on what usually gets called global priorities or existential risk research at universities or think tanks. And this research community, basically the focus is, if we do something that really messes up civilization, if we do something that sort of is like bad in a sort of world historically important sense, what will it be and what can we do to avoid it? And there's this emerging consensus that's been showing up in the last few years in this community, which is that the transition to broadly capable AI, not necessarily like conscious AI or human-like AI, but just effective AI, is incredibly important. That making sure that future broadly capable AI systems are safe and robust and controllable is one of the most important issues that humanity has ever faced. People are very explicitly saying this is kind of on par, at least as important as climate change and pandemics and nuclear proliferation as a sort of serious global priority. And as of recently, especially since GPT-3, this community has been pointing to large language modeling research as the canonical example of the thing we should be worried about, of the trend that is pointing toward potentially dangerous outcomes. So this is nuts. This is like, it's not normal in science that you sort of bump into another pretty serious research field that is arguing that what you're doing is potentially the worst thing in the world. So I think we should let's talk about this a little bit more before I get back to the main meat of the talk. So this is obviously a little bit fringe relative to sort of normal conversations in CS, but this is not nothing. I've been able to find about $75 million in grants just from like the first organization I checked that gives grants in this area. And also OpenAI and DeepMind have pretty large teams with pretty significant influence working on sort of catastrophic risk from AI. And I think this is worth paying attention to, even if you don't think that the arguments hold, even if you don't think that there is a credible risk here. Because if these points are right, we should obviously be paying attention to not wreck the world. And if they're wrong, we should be paying attention to try to really come up with clearer and more persuasive rebuttals. Because if we don't, I think there's a real risk that this could derail all the positive potential of the field. As just one example of this sort of starting to catch on, there was a Prime Minister's speech in the UK recently where the Prime Minister sort of argued that one of the major issues that he wants the government to be preparing for is catastrophic risk from AI. This is starting to reach sort of high-profile decision makers, and if we've got lots of people arguing that sort of progress in AI is going to wreck everything, and no one arguing the other side persuasively, this could lead to really major social backlash, really major regulation that prevents us from doing all of the actually valuable stuff we want to do. So just quickly, I know this is sort of a detour from the talk, but like what are these arguments about? I think there's sort of roughly 4 threads of argument for sort of why advanced AI can be dangerous. Again, none of these involve systems that are conscious or self-aware, just that we get human-level performance at language and reasoning with language and planning with language. So roughly the things that a lot of us claim to be working on. I think just to quickly go through the 4, like these 4 rough arguments. The paper has more pointers to kind of actual writing on this. There's this idea that an organization that has accessed highly capable AI could be both very profitable and have very good tools for persuasion and surveillance. This is kind of maybe an extrapolation from where big tech is already, but a pretty dramatic one. You could wind up with an organization that is really genuinely unaccountable, where they have sort of so much power and so much influence that no government or no other government, if they're a government, is able to meaningfully change their behavior. And while they have them become powerful enough, they have a really significant say in the future of the world. This could be very bad. And this is just sort of about any organization that has access to sort of truly effective, reasonably general purpose AI early on. There's this classic kind of alignment risk story. The idea here is that if we have systems that we either are trusting to make high stakes decisions, or that are capable enough and strategic enough that they can sort of make high stakes decisions for us, then we need to make sure these systems are trying to do something that we want them to be trying to do, and that their understanding of what we want generalizes to new situations, generalizes out of domain. And both of these are potentially hard problems. And the literature on sort of why they're hard actually focuses on QA systems as a canonical example. So it's sort of, you don't need systems to be sort of robots for misaligned goals to be potentially quite bad in capable enough systems. The idea of instrumental subgoals is sort of an argument for why alignment can be difficult, which is that pursuing a reasonable sounding goal, like giving accurate answers to questions, if you're pursuing it thoroughly enough, if you want to be as good as possible with as high confidence as possible, you can develop these implicit subgoals that you want to survive, you want to acquire resources, things like extra compute capacity, and you want people to not interfere with you. And these goals, if sort of systems pursue them very aggressively, are bad for us. And finding a way of specifying an objective, a training loss, something like this that doesn't do this is surprisingly hard. And then finally, I think sort of the 4th ingredient of this is that it might be hard to see some of this coming. If you think that deep learning is a viable path to actually developing these capabilities, We sort of know that deep learning systems are difficult to interpret with confidence. It's hard to say really with high confidence if I know what a deep learning system is doing and why. And so it'll be difficult to know when a system is dangerous or when a system is safe. And organizations will probably want to be first for the reasons that I mentioned earlier. And so organizations have an incentive to build systems without being dead certain that they're safe and take potentially unacceptable risks. So that was a sort of high-speed detour through this very weird literature that's popped up recently that I think bears a lot on this question. But to wrap up, I think the impacts of the technology we're building could become much, much greater if we start to actually succeed at a lot of our goals. And to the extent that we can influence the outcome to make sure these impacts are very good instead of very bad, we should try. Making these impacts net positive is going to require some planning and some research to happen by the time that it's possible to build this technology. Because sort of once it's there, according to a lot of these arguments, sort of things get weird and bad pretty quickly in ways that are hard to manage. And so I think we're unlikely to be able to have the kind of influence we want if we don't see this technology coming. All right, so hopefully between either the very concrete self-interested argument or these much weirder stuff, you have some intuition that it is valuable for the field to have a clear consensus about what the state of the art is that avoids both hype and underclaiming. So how do we get there? What do we do about the problem? So my main argument here is that actually this is pretty easy. That most researchers who are sort of participating in the community either have PhDs or are working on PhDs. And one of the main things you learn in the first couple of years of a PhD is how to not overclaim. Is you write your first paper and either your peers yell at you or your advisor yells at you or your reviewers yell at you or your audience yells at you. So if someone is going to point out if you make any claims that aren't justified by your evidence, that are generally sort of too strong or too boastful or too confident. And I think this skews very much toward avoiding hype and avoiding overclaiming, but I think all of the same skills of reasoning about evidence apply in almost exactly the same way to underclaiming. So I think if we acknowledge this is a problem, if we look out for it in peer review, we can mostly solve it. I think there are a few things that would be helpful here to sort of come up with some concrete action items to work on. So one of these, I think there's enough of this underclaiming follows a very clear pattern in discussion of citations and things like related work sections. There's a sort of fairly concrete rule of thumb we can apply that should catch a lot of common instances. This is my proposed sort of rule of thumb for reviewing and writing. So if you're describing a failure of a machine learning model on some evaluation, you want to make it clear what kind of model has failed. Don't just say sort of current deep learning fails, say that BERT fails. You want to say, if that model is significantly behind the current state of the art, and you know that, you should say that. You should say sort of, hey, BERT fails here in embarrassing ways, but GPT-3 is what someone would actually use if they were trying to build a system. BERT is somewhat dated in this domain. And if the evaluation was deliberately set up to trick that model or something like it, you want to say that. You might say, hey, Roberta performs poorly on that data, but the data was collected to fool BERT, and so we should not be too confident about how much the data actually reflects normal performance. That's the proposed rule of thumb here. Hopefully this will catch some of the easy cases. And there are some research agendas that I think will help us sort of get at the root cause here, help us kind of slow down the hype cycle, which is, I think, causing these reactions and causing the skepticism. So I think getting better at evaluation and getting better at just sort of making sure that the positive results you report are true would be really helpful here. So this looks like better task design, better crowdsourcing, better benchmark platforms, better statistics, and better publication norms, sort of all of the kind of careful science type work that happens in NLP. I'm not contributing that much to this disposition paper, but I think a lot of this kind of work can make a big dent in this problem. There's a very specific thing that I think would be very helpful that I think we're close to being able to do, which is making our analysis techniques more responsive. The idea here is that when you do one of these analysis projects, Bertology projects, sort of robustness testing projects, very often what you're doing, what you're producing, is a method or a data set that you can apply to a system that gives you sort of interesting, interpretable observations about where that system fails. And very often this method can be mostly automated or entirely automated, so that once you build a system to analyze BERT, you can very immediately reuse it to analyze dBERTA or modify it only very slightly to analyze GPT-3. And I think actually building computational tools, things like leaderboards or web platforms that do this automation, that let you apply old analysis tools to new models and vice versa, can be really, really helpful. I think it would be great if sort of when someone publishes a new Bertology paper showing a failure in sort of last year's systems, that we can just click a button and say, hey, do this year's systems fail in the same way? That's very valuable knowledge. Orb, this reading comprehension benchmark from AI2, I think does something that's fairly close to the idea. It unfortunately hasn't really caught on. This has been out for a year or so without a lot of traction. But I think there's room to experiment with this, room to use tools like Hugging Face to try to figure out how to do this well. And then finally, I think research on forecasting and scaling laws can be helpful in a couple of ways. So this is work that attempts to extrapolate sort of how does performance on NLP tasks change as we get more data or more compute or we make our models bigger. I think there's been a pretty good track record in language modeling and MT of being able to actually make these forecasts. And when we can make these forecasts, I think they really can push back against the hype cycle. I think the idea here is that if we forecast a result and then observe that result, we should be pretty confident that it's true. We don't need to be too skeptical. If we forecast a result with a trustworthy forecasting method and observe something that's wildly off the trend, that's sort of way too good, we should be very skeptical. We sort of know where to target our skepticism. And also, obviously, this helps us prepare for longer-term risks if we can extrapolate sort of like at what point we start really hitting human performance on various measures. But this only works if we can actually measure progress on the things, on the trends, on the metrics that we care about, which is work here is very limited so far. I think we've only really have kind of clear positive scaling law results for 2 or 3 metrics in NLP. So I think trying to build out this research area, I think would be quite helpful. All right, so that's the end of the argument. So I think we're not in a great position to recognize progress as a field. Sort of just the discourse about what the state of the art can do isn't super healthy, isn't super evidence-based in a lot of cases. This is dangerous for a few reasons, both pretty concrete and short-term and pretty speculative. I think it's not too hard to fix, so let's go do something about it. And thanks for coming to the talk.
Thank you, Sam. Thanks for this great talk. So now we have time for questions. If you want to make a question, just you can do it in the chat or raise your hand, and I'll give turns. You cannot see the chat, right?
I just opened it, so I think I can now see it.
Okay. Yeah, people is clapping. I didn't know there was a tool to clap. Sorry, this tool is new to us. So, anyone for questions? Okay, so while people is thinking questions, first of all, I really enjoyed the talk. For me, it's an eye-opener because I never thought about this underclaiming thing. I need to be honest. So the hype was something which worried us because possible backlashes, but I wasn't aware. And actually, well, you touch it in many different topics, all of them very interesting. And I agree in general in the message. So I was really convinced. So that underclaiming, yeah, I really liked it. And underclaiming has to be taken into account. And actually, it could be a bit worse in the sense that you showed examples from actual papers in your cases. But actually, these kind of things then go larger, and they become conversation in research groups, and then they become conversation in people working in related fields, and actually they reach politicians. And I think this. So it may be, so when you see this claim in a paper, somebody wrote it, so took the time to write this underclaim. But when you are chatting in about research, people are much sloppier in what they say. So these kind of ideas, I think, this kind of rumors, they kind of expand. So I really believe this is a risk.
Yeah, I think that's right. I think there's a sense that yeah, sort of, I don't know, hallway conversations at startups and some labs can be very, very positive, can assume, oh, we built AGI, we solved everything. I think in the same way, sort of conversations in some kinds of research groups, especially that are a little bit farther removed from very large scale work can be sloppy in the other direction. And yeah, that's harder to point to, it's harder to write about because I don't have evidence to cite. But I think that is yeah, a real way in which this can show up.
Yeah. So I had some specific sort of things. Maybe you mentioned a paper, so I think it would be good to have access to the paper. Oh, I see now
Yeah,
questions.
yeah,
Just 1 minute, I'll do just one very specific question. When you
yeah.
mentioned that there was, in the first case, that there was this work based on BERT, which I kind of assumed, because again, sloppiness. I kind of assumed it was done with pre-trained language models, but you, the one on question answering, in the first case that you mentioned.
Yes.
Yeah, they did results, yes. And then you mentioned that you actually, or somebody in your lab or somebody did actually test it with newer pre-trained language models, and that the effect was not there. Could
Yeah,
you?
yeah. So the
Could you elaborate,
paper
please?
actually, so yeah, the paper is it's the same title as this talk. It's on archive. So I have some slightly older results in the paper. I'll update it when I next get a chance. All right, so yeah, here are the older results. This is less compelling than the newer thing. So this is, I think, there are sort of these two metrics of performance. I think what they're finding is where ReasonNet, where sort of the best 2017 model was getting 40% accuracy on this modified data, sort of newer systems are getting 70%. So there still is a gap, but we just made a lot of progress by 2019. But these are the newer systems we had results for then. There's some results by Max Bartolo on Twitter. Actually, I think I would need a few minutes to track this down. So if anyone sends me an email, I can find it.
Yeah.
But Max Bartolo, University College London, ran some of these results with something newer. I think not brand new, but I think maybe Roberta, and got a much better number. I think maybe a 5% gap between squad performance and performance on these held out sets.
So this is
so
yeah. So there is a lot about how scientific ideas and scientific messages are circulated. They're not so different from what happens with other kind of news. So when you have a negative news on the press, everybody talks about this, and maybe 1 or 2 weeks later it's falsified. It was not true, but maybe it doesn't get so much press attention because the first one was more noteworthy. So that could happen here. That this one had this paper with lots of citations, and then the evidence which shows that this is not this doesn't have so much anymore. It's just scattered in Twitters and tweets. And, yeah, that's interesting.
Yeah. No, I think that's right. I think this is why I think we really want to be careful about policing these claims when they show up, rather than rebutting them. Just because, exactly as you say, it's very hard to get rebuttals to have the same attention and the same staying power as the original claim. All right, it looks like there's some. Should I be going directly into this? It looks like there's some questions.
Yes. So I don't know if you can call the people if they want to do it on the mic, or you can read it as you prefer.
Sure. I guess, yeah. I don't know. Yeah. I guess. Ada, do you wanna ask your question, or should I go for it directly? All right. Sure. Okay. So it seems like there's something that's lost in translation between disciplines. In CS, we have this concept of framing something as a task to be solved. The word solve rubs some linguists or computational linguists the wrong way. What do we do about this? Yeah, I don't know. Yeah, I don't know that I have a great answer here. I think this is important and a little bit removed, and important and fits into this discourse a little bit removed from the exact claim I'm making. Yeah, I think I'd accept that sort of the scientific goal of sort of understanding the limits of what, or like understanding what computers can do with language and how and why, is thing where there's not really a meaningful notion of solve. It's not really a meaningful sort of endpoint for more scientific research. But I think there is something that this idea of sort of solving a task is still hard to pin down precisely, but I think there is still something meaningful there, that there are sort of real world applications or real world systems we can build with language that are or are not sort of reliable enough to actually be useful in some setting. And it is, I think, reasonable to keep in mind, so how close are we to hitting various milestones in making systems that actually solve problems for people that people would actually want to use. So I think it's yeah, I guess I want to say, yeah, this often is tricky to pin down. It often gets close to scientific questions that are possible to pin down. But I think just because we can't pin this down really precisely doesn't mean there isn't something real there, that there isn't something we're actually making progress toward. All right, username Surangika. Do you wanna read this out, or should I go for it?
Okay, so and thank you for the great presentation. So this is actually based on some recent experience. So we were trying to do some empirical evaluation on multilingual models, especially for the low resource languages, to see how they perform on extremely low resource settings. So what we realized was we try to consider a very broad research, evaluation plan that involves data from different languages, different domains, and also what when we're trying to analyze results, what we realize, so it's very difficult to explain the results with respect to different domains, different languages, and the coverage of the language in the model and the amount of data you will use to fine tune the model. So I don't know, is it really possible to consider all these factors and explain the performance of a model in a realistic manner?
Yeah, I mean, I think these are all important caveats. I think any sort of numeric result like this of sort of just how good a system is at a task is inevitably going to be grounded out to, all right, what language or languages are we studying? What text source or text sources are we studying? What data regime are we in? Like, how much data or knowledge about the task did we use? And that's unavoidable. I think there's no sort of truly neutral, agnostic way of measuring how good a system is at language. But I think I don't think that's an enormous pitfall. I think it's still possible to measure progress toward things we want by just saying, all right, look, here are a handful of use cases that we care about. Here's how they tend to correlate with one another. Systems that are good at X are often good at Y, and just look at a few measures for specific targeted use cases. So here, for example, Squad is measuring how well we can do at reading comprehension in a single domain with reasonably straightforward literal questions with large training sets. And I think just kind of finding reasonably concrete, reasonably fully specified target applications or target evaluation settings and following those is still valuable and viable, even if we're not sort of factoring them out. Yeah, thanks.
Sorry, Sam. Time-wise, I think there are two other questions in the chat. Time-wise, is it okay if we go like 5 minutes longer? I mean, it depends on you, of course.
Yeah, that's fine with me. I think 5 minutes is about what I can stick around for. Cool. Yeah. All right. So, Konstantin, do you want to read out loud, or should I jump in?
Yes, sure, I can try. So underclaiming seems to be related to our lack of research on ethical, ecological, and explainable AI, from my perspective at least. So how can such research be conducted while also avoiding underclaiming?
So I don't know there's a conflict there. I think there actually no, okay, I think there's a slight tension. This gets back to I think this point. So I think one pressure in favor of underclaiming is this idea that we don't know how to deploy our systems responsibly. And so there's this sort of perceived need in NLP research that I'm generally on board with. I think that we should be doing a lot to try to slow down the pace of deployment of a lot of the technologies we're building, just because they cause pretty real harms that I think we're not very good at mitigating, might get better at mitigating in the foreseeable future. But I think this instinct to try to slow things down by doing underclaiming is just wrong. Just doesn't actually work. Isn't actually a responsible strategy. And I think if you try to think through this, you'll probably, I think that's not that tricky a claim to defend. And so I think just we want to be, I think the thing, sort of the arguments we should be making to stakeholders, to people doing deployments, to regulators, is just there are big risks and big unknowns about the social impacts, environmental impacts of the things we're building. That should really limit sort of what we do with them and how we plan out deployments. But even so, not let that bleed into claims of what the models can do. We can say sort of, hey, we have these systems that are really incredibly good at doing X, Y, and Z things with language. They're bad at a few of these things. But the real issue is that we have system technologies that are pretty good, but that we can't deploy responsibly. And we need to figure out how to deploy them responsibly in order to get these benefits without getting the risks, and just sort of give the slightly more nuanced picture when we're having these conversations. I don't know. Does that fit the question?
Yes, thank you.
Great, thanks. All right, Utku, do you want to jump in? I got that right.
Hi, thank you for the talk. So what I think is that, like, from your talk, the hype is not the problem, but hyping other stuff, like saying like stuff like, oh, we solved everything is the problem. But instead, like, yeah, we can try to focus our effort to hyping like small advancements, incrementality, or I don't know, maybe like replication reanalysis. But what I saw in general in conferences or in publications or in journals is that they either award really like best papers, or the papers that has like a nice titles and nice like result parts. So
yeah.
Even this talk, workshop, the hype is the problem is a bit like hypey title, right? So
Yeah.
So like, what can we do about this?
Yeah, I don't know. It's tricky. I think this plays into all of it. It plays into this idea that sort of pushing a little bit towards slow science is valuable. Sort of anything we can do to cool down the conversation, to figure out how to get peer review to work a little bit better, figure out how to get evaluation of research to work a little bit better is super valuable. And that's really hard. I'm sort of focusing on these ideas like this rule of thumb about how we cite work, and these proposed research agendas, just because I think fixing peer review, fixing the discourse overall is hard. So I think I'm focusing on targeted solutions just because I think that's where it's easy to make progress. I don't know how to fix the conversation more broadly to sort of emphasize the right things. Also say I think I've mixed feelings about some of these issues. So I think there is a real sense in which some of the work that can have really high impact about things like model efficiency and reproducibility and bias measurement and mitigation that have an enormous impact on sort of whether we can actually use the technology we're building are really important and maybe don't get enough attention. At the same time, I think some amount of hype is obviously the wrong word. I think hype by definition is wrong, but I think some amount of excitement is justified. I don't know. My impression is like the results from, for example, sort of GPT-3 or XLMR, like what those systems were able to accomplish, I think is really incredible. It's something I would not have predicted we could have gotten in 20 years when they first came out. And I think it's reasonable to be excited about some of the actual progress we're making, as long as we're careful to be sort of honest about what that actually is and what the limits are.
I see. Thank you. Yeah, I agree with GPT-3 point exactly.
Yeah.
Thank you.
Cool.
Okay, thank
right,
you, Sam, and thank you to all attendants. It's been a great. So I'm still thinking about some of the things that you raised, because you touched in many things, and one thing which is happening, at least in Europe now, is that politicians are aware of these risks of AI, and they are looking at experts like ourselves or yourself, who are thinking about which are the real issues. And I think it's actually very timely, this talk, at least in our case, because in Spain they're also trying to regulate these things, and also in Europe. So to help them weed out which are the real dangers and which are not the real dangers, I think that's really useful. Okay, thank you very much. And
all right, thanks so much for coming. And yeah, if you have more questions, send me an email. Thanks so much.
Okay, thank you. Bye to all.